Oh. Good evening, ladies and gentlemen, and welcome to the Space Telescope Public Lecture Series. It is my joy and pleasure to be your host. I am Dr. Frank Summers of the Office of Public Outreach. On your way in, you could have grabbed a lithograph. Tonight's lithograph is the Interacting Galaxies ARP 147. There are a lot of interacting galaxies that have these ARP names because ARP created the catalog, okay? If you want to learn more about interacting galaxies, you can turn over on the back and read about them. If you did not get one on your way in, they're down here on both sides. Grab one on your way out. Tonight, I guess my pointer's gone. Tonight we have the wildest weather in the universe, a very catchy title, which I think is partly responsible for so many of you showing up today, by Hannah Wakeford. Next month, we have another very catchy title, Mapping the United Federation of Planets, an Astronomer's Guide to the Galaxy. And yes, that is a Star Trek reference, and yes, Star Trek will be part of the talk next month, although it will be used in a scientific context for mapping the galaxy. In April, we do not actually have a title, so I gave it the title Lovely Plumage on Europa. Susanna and I chatted on the phone today. She said, I'll talk about the plumes on Europa. And I said, oh, the lovely plumage story. And so I wrote that as a placeholder, and she was supposed to email me an actual title, and I forgot to, I don't know if she actually did, because I forgot to check. So that it's about the plumes on Europa. Okay, it'll be a cool talk. Susanna's a very good speaker. All right, and in May, a talk that I've been trying to get for a while, Andy Fruchter has agreed to talk about gravitational wave astronomy, the new way we're going to view the universe with gravitational waves. So you can find all about all our upcoming talks on our website. That has on the right the list of the upcoming talks. On the left, we have links to our webcasting and our recordings of them on YouTube. When we are live, you can click those and go directly to those. You can also sign up for email. If you just go to your favorite search engine and type in Hubble Public Talks or Space Telescope Public Talks, you will find this web page. If you would like email announcements, actually you don't, you sign up at the website. I mentioned that down the lower left is our email server, listserv, so you can subscribe or unsubscribe there. If you have comments or questions, you can send it to the email address publiclecture@stsci.edu. Social media. Last month I said I'd start including the web telescope accounts, and here they are for you. We have Facebook, Twitter, YouTube, Instagram, and probably more for both Hubble and Webb, and some for the Space Telescope Science Institute as well. I do a tiny bit of social media on a blog and Facebook and Google and Twitter, so if you want to hear more from me, you can do that. The observatory. The question is whether or not the weather is permitting. Did somebody notice whether their clouds were up when they came in? Oh, somebody's giving me the thumbs down. Okay, it was a questionable, and Irini may have emailed me her decision by now, but the audience gives us a thumbs down, so it probably will not happen. Okay, but they do an open house on Friday evenings. If you go to md.spacegrant.org, you'll find that web page over there on the right. And in that box where it says observatory status, each Friday by like 5 or 6 p.m., they update it with the information as to whether they're going to be open that Friday evening. Okay? So check that out. Sorry that we probably won't be able to get that in tonight. And now, News from the Universe for February 2018, in which we answer that amazingly scientifically detailed question, do black holes burp? Now, massive galaxies are known to have supermassive black holes at their very core. This is a massive galaxy, and there is a supermassive black hole at its core. But of course you can't see it because the supermassive black hole is tiny compared to the galaxy. But these supermassive black holes can cause huge emission. This one is called Hercules A, and when viewed in radio light, it looks like that. From that tiny supermassive black hole in the core are emitted huge jets of emission that spew out across the galaxy and beyond the galaxy to form these giant radial lobes. Now, not every supermassive black hole is in this phase when there's giant jets of emission coming from them. Sometimes it's a little harder to find. They're not always in this emission phase. And what we want to know when we look at the cosmological history of these supermassive black holes is how often are they on when there's material falling in and stuff that's being emitted back out, and how often are they quiescent? How often are they quiet and they're not really emitting? That's one of the things that the cosmologists really want to understand about these black holes over time. So here is a Hubble image of a galaxy SSS J1354, okay? That's just its catalog number in the Sloan Digital Sky Survey. And this is the Hubble image of the galaxy, and the galaxy we're interested in is not the one at the top, but it's actually the one at the bottom, okay? The one at the bottom has a supermassive black hole that's active. Now, what you will notice between the top and the bottom is that there's sort of a striation material that seems to be flowing down from the one at the top. These two galaxies are believed to be interacting, okay? And when galaxies interact, sometimes material from one galaxy can accrete onto the other galaxy. And so what we wanted to know, what we found out when looking in X-rays is that the supermassive black hole in the bottom galaxy is turned on. It is in an emissive phase because here is the Chandra X-ray Observatory. Now you got to look carefully, all right? There's Hubble and Chandra. Okay, you can see that purple X-ray emission that identifies what's coming from that supermassive black hole. So let's magnify that and give you a little bit of context here. What we see here is that the material is coming from it, and that white burst above it appears to be material spewed out of the supermassive black hole. Matter of fact, what they tell me, and it's kind of hard, I couldn't really see it in the image, is that there are two periods of emission. And given the speed that this material is traveling away, that it was in emission and then 100,000 years of being quiet and then another emission. The hypothesis, the best explanation for it is that these two galaxies interacted, material flowed in, all right, and started to spiral in on the supermassive black hole. Some was spewed out, and then it went quiet for a while, and then some more was spewed out. All right? And in the press release, they call these burps from a supermassive black hole. I kid you not, in the actual press release, they use the word burp. But is it really a burp? And I would say no. Because when you or I burp, it comes from inside us and spews out, right? But material doesn't come out of a black hole, right? Even light can't escape from a black hole. It's not the supermassive black hole that is burping, but rather the material is falling onto an accretion disk around the supermassive black hole. Some of that material goes into the black hole. Some of the material gets flung back out from the accretion disk. Okay? So I would say, just to be a little technical, that it's the accretion disk that is burping and not the supermassive black hole. So that's my answer to that question. Our second story tonight, the launch of a new era. Way back in the 60s, in the Apollo era, we had the Saturn V rocket, the most powerful launch vehicle that America has ever had. And this actually is the launch of Apollo 11 from Kennedy. And the Saturn V rocket was retired back in 1973. It was followed by the space shuttle, This, by the way, is the launch that carried the Hubble Space Telescope into orbit. And you can see the the launch on the right, but also you can see another STS actually testing on another launch pad at the same time. Okay, and this was also incredibly powerful, but it had to carry the space shuttle up. So the payload that could be inside the space shuttle was considerably smaller. And so what people have been looking for is a really big boost to get into space. And so NASA has plans for a wonderful system coming up. But in the meantime, we have developed commercial companies, such as SpaceX, Elon Musk's company, SpaceX. And this is their workhorse, the Falcon 9 launch booster, so-called 9 because there are 9 engines in this booster, okay? And they have been launching these for several years and putting satellites into orbit with it. But it wasn't powerful enough. So what Elon Musk is a little bit ambitious, and what does he want to do? He wants to make the world's most powerful rocket. This one is the Falcon Heavy. And you will notice it looks very much like the Falcon 9, except it has outboard motors on it, which are, in fact, 2 other boosters, identical boosters. So there are 27 engines on this 3-pronged rocket. All right, and they did a test firing a week or so ago, and they didn't actually launch anything. They didn't actually go off. They did a test firing to show that they could launch all 27. They could fire all 27 engines together, and today they did the test launch. What was the payload? The payload was from Elon Musk's other company, the Tesla cars, and it was a Tesla Roadster, a cherry red Tesla Roadster with a dummy in one of the SpaceX spacesuits in the driver's seat, okay? This is the actual Roadster that was on the payload today, okay? And did it work? Yes. Oh yeah, yes it did. Here is the footage released by SpaceX showing the Falcon Heavy launching from the space pad. And once it got up, the 2 side boosters separated, all right, and they came back and landed vertically. I never get tired of seeing that, okay? SpaceX has been doing this for a while. I never get tired of watching this. Now, the center booster was supposed to land on a platform out at sea, which SpaceX has done before, but there is no confirmation from SpaceX that it landed safely. There was a disruption in the video feed that makes people a lot of speculate that it did not land successfully. But there has been no confirmation as far as I've heard from SpaceX. Okay. And then they had the payload deployment. So this is footage of the Tesla Roadster being deployed into space. Okay. Yes. All right, and this is my favorite shot. This is a shot over the shoulder of the Tesla Roadster in orbit around Earth right now. And you'll notice it says on the dashboard, "Don't panic," which is an homage to Hitchhiker's Guide to the Galaxy. And Elon Musk says, yes, there is a towel in the glove box, for those who know. All right, and while this is a lot of fun, it actually makes for a really interesting point in our history of space. Because right now, the most powerful launch vehicle on the planet is not from a nationalized space agency, but it's from a commercial space company. And that's a new era in space flight. All right. Now, of course, NASA has planned the SLS, which will be more powerful than the Falcon Heavy when it goes. But for now, SpaceX has the most powerful launch vehicle, and if you want to get something heavy into space, they're the people to go to. So this, I love the audacity of Elon Musk, and I love that he has a sense of humor. So this was fantastic.
Now, will that orbit the sun eventually?
All right, so yeah, I'm not exactly sure the timing of it. It's got to get out past the Van Allen belts, and then the second stage will fire and try to put it into orbit around the sun that goes out to the orbit of Mars. So we'll have a Tesla Roadster orbiting, driving around the solar system, sort of like interplanetary NASCAR, but it's only a one-vehicle race. And actually, it'll have quite some frequent flyer miles, but it's still actually a low mileage car, right?
The original picture.
You want to go back where? Here?
Original picture where it was draped over the top of the.
That? Okay. You want a picture of that? Okay, it's available on the internet because that's where I grabbed it today. Okay. Our final story for tonight. You have to imagine if the Falcon Heavy could not only go interplanetary, but could go interstellar, all right, and could shift wavelengths. All right, our outreach program is now called the Universe of Learning, NASA's Universe of Learning. We used to be funded as the Hubble Outreach Program, or the James Webb Space Outreach Program, or the Spitzer Outreach Program, or the Chandra X-ray Observatory Outreach Program. They were associated with the missions. Well, NASA refunded things in a multi-mission way where our outreach is about the astronomy and it covers all the various wavelengths. And so, for example, one of the things we've been doing for years, and actually the Spitzer folks have been doing a lot of too, is doing sort of a slider here where you can slide from the visible light view on the left to the infrared view on the right. And as you move that slider across the screen, it shows you how the universe looks in visible and infrared. And we found this to be a very powerful thing to do. All right? But, that's doing it in 2 dimensions. We wanted to take these 2 images of the Orion Nebula, on the left from the Hubble Space Telescope, and on the right from the Spitzer Space Telescope. And we wanted to do that same thing in 3D. So one thing you notice automatically is that the Spitzer image covers a much larger area. It's infrared radiation, which comes from cooler gas, which spreads out further in the nebula. You can actually see the whole bowl of the Orion Nebula over there. There's also more stars in the infrared because you're seeing the fainter, cooler stars that shine mostly in the infrared. But when you get down into the detail, Hubble has higher resolution, and you can see those bow shocks and those protoplanetary disks and all sorts of cool fine-grained structures in Hubble. Of course, you can't see it at this resolution, but you'll see it in a second, that you can't see in Spitzer. So what we did is we built a model of the Orion Nebula for the IMAX film Hubble 3D using visible light. Then we rebuilt the model using the Spitzer data in infrared. And then we're going to fly you into it. So, Thomas, can we take the lights down a little bit? All right. So we thought that was a considerable success, being able to show you in 3D that what it looks like from the Hubble visible light image, what it looks like in the Spitzer infrared image, and you get a real feel for the different structures that we see and inherently the value of multi-wavelength astronomy. All right, so now we go to our featured speaker tonight. And our featured speaker is Hannah Wakeford. She got her, let's see, let me just find things. All right, she got her PhD in physics from the University of Exeter. Previous to that, you were at the University of Wales in some city that I'm not sure I can pronounce. So you'll have to pronounce it yourself, okay? And she also worked at the University Center in Svalbard in the Arctic at 78 degrees north latitude. Yeah, that's further north than I'm sure anybody of us have ever been. She can tell you about that. If you thought it was cold here last week, no, you don't know cold. She has worked at the NASA Goddard Space Flight Center as a NASA postdoctoral fellow after getting her PhD, and she came here as the 2017 Giacconi Fellow here. And one of the most important things is that she has extensive experience in public outreach, working on a podcast called Exocast about exoplanets, as you might guess, as well as writing a blog called Stellar Planet. All right. And she can tell you more about that, but I'm looking forward to seeing how she performs. Hearing her tonight, ladies and gentlemen, Hannah Wakeford.
Let me just switch this over for everybody. You can watch me type in my password, apparently. No, we're good. Okay. Well, all right then. Hello, everybody. This is a great crowd. Brilliant. Loving it. So I'm going to take you on a little bit of a journey across our galaxy through different worlds and looking at some of the wildest weather that we have actually been able to look at and understand. I'm going to start our journey a little bit closer to home. This is our wonderful solar system to scale, and I love this picture because it really puts a good perspective on our planets and ourself. Right down here, tiny little dot. Poor Pluto and the Plutoids out there. This is our solar system encapsulated in a single image. And I'm going to take you through what makes up these planets, what's really interesting about these planets, and where weather comes from. Now, you can't have weather without a little bit of gas. Mercury has really only got a little bit of gas. Mercury's weather comes from when the sun bombards it with particles. The sun's particles come out in the solar wind and they hit the surface of Mercury. There's nothing getting in the way of that. Just slams into the surface. That actually then causes other particles to be lifted up from the rock. And that forms Mercury's atmosphere. It's not permanent. It's very intermittent. It only has this gas around Mercury at very specific points where the solar wind has hit it. We don't really call that an atmosphere. So it doesn't really have weather. What Mercury has is the sun's weather, and it lives inside the sun's atmosphere. Venus, on the other hand, has something very, very different. Venus has an atmosphere which contains lots of different materials, but it's one of the smallest percentages of these materials, this SO2, sulfuric acid, that causes the most trouble for Venus. This is a gorgeous image of Venus from the JAXA, the Japanese Space Agency satellite, which is in orbit around it now, called Akatsuki. And if I just take a next look at that, we can zoom in on these cloud structures that you have in the atmosphere. This image is taken in the infrared. And what you're seeing from those dark bits there is this sulfuric acid in the atmosphere. It extends for hundreds of kilometers. It makes up 0.015% of the material in the atmosphere. But if we were sitting in the atmosphere of Venus at the same pressure as we're all feeling right now, a centimeter per square inch, we'd be sitting right in the clouds, and we would have melted away. This stuff is horrible. It would melt through your skin in less than a minute. It would get down to the bone in 2 minutes, and there wouldn't be much left of us. So it's incredibly difficult for us to understand and study Venus because it's such a horrid, harsh environment. When you get down to the surface of Venus, it's 90 times the pressure that we feel here. 90 times. That's going down very deep into the ocean. Now, humans have scuba dived that deep, so the pressure's not the thing that's going to kill you, and you've got to get through the sulfuric acid first. But it's also really hot down there. It's 700 degrees. Ugly little sister, right there. It's not a nice place, and that's some very strange weather. But it's not the strangest in our solar system. Some of the strangest phenomenon that we have aren't permanent, like Venus's sulfuric haze that extends throughout the atmosphere, but they're intermittent. They only happen every now and again. And one of these we actually see on our neighbor Mars. What happens on Mars every now and again is a global dust storm. What you're looking at is 2 images that were taken just months apart. One which is nicely labeled for us. We can see all of these different features on Mars. And the next one, just a couple of months later, everything is wiped out. You can just see the shadow of the edge of this Eden region. A global dust storm can encompass Mars in just a week. And we're actually expecting another one quite soon, so I don't know how Curiosity is going to be feeling about that one. But these storms are intermittent and they go away. So it's a very strange phenomenon that we don't actually understand. We think it's got something to do with the gravity. But people are still trying to work that out. And it's really great that we've got these different missions that are going into orbit around Mars, and we've got missions on the surface that can monitor these for a long time, so we can see these chance occurrences. So that's just another strange thing. Those are our terrestrial planets. These are small rocky worlds. What happens when we stick a load of gas on top of that? Well, you get something like Jupiter. Isn't that gorgeous? I want pictures like this of everything. This is a beautiful image that was taken with Juno, which is currently in orbit around Jupiter. And you could fit 3 Earths in the side of that storm. That is a hurricane the size of 3 Earths. That's hard to imagine. That's not something you can really put a scale to. To try and help out, this is Jupiter looking down at its pole where you can see these gorgeous vortices. This is just dynamics in action. This is fluid dynamics at its core. And you can fit 11 Earths across that. So the storm around near the equator, just south of the equator on Jupiter, is 3 times the size of the Earth. Jupiter itself is 11 times the size of the Earth. That is a humongous storm. You do not want to be caught in there. Not only is it a huge storm, but actually some of the scientific evidence has shown that it's heating up the atmosphere above it. So the storm itself is colder than the air that it's generating above. And that's really interesting for us to try and understand, that this massive hurricane is generating heat high up in the atmosphere. How is it transferring that heat, and where's it going afterwards? Is that what's sustaining the fact that this storm is still there? Now, Hubble Space Telescope images have shown that this storm is changing size. It's kind of fluctuating. But that's over many years' timescale. It gets bigger and smaller, and we're like, oh, it's going away, it's going away. And then it comes back full force, and you get a picture like this, which was taken just last year. So it's a truly amazing phenomenon in our solar system. But you can see the pole here, and I want you to really focus on that pole. Look at all of these gorgeous vortices. Look how small some of them are. Look at them spiraling down. This is the pole of Jupiter. If we go to the next planet, Saturn, the pole looks very different. There's a strange giant feature. And if we zoom in, take a look at that, it's formed a beehive shape. Nature does this very naturally, and it's all about the way material cools and expands. But if we zoom in even further, we can see that there's this hurricane right at the center. We didn't see that on Jupiter. There wasn't this central storm, this vortex in the center of the pole like we would expect, everything spinning around. There was lots of them, lots of little poles. Here we've got this ginormous storm right at the pole of Saturn, inside this weird shape. And that really threw people for a while. We're trying to still work on simulations to see why this is forming, what temperature the material would have to be, what would it be made of to form this perfect shape. And this came from the Cassini spacecraft.
Are these real colors?
These are modified color. So this is an infrared image, this is an optical image, and this is very much modified. The blue that you see there actually is the rings. So we're looking at a slant edge there, and you're seeing the rings in the distance in this image. So these are all enhanced color images of Saturn. This one's a little bit closer to the truth. But that's not the coolest place in our solar system. I'm biased, but the coolest place is Neptune. Neptune has winds that reach up to 1,300 miles per hour. 1,300 miles per hour. And that's what you're seeing here. This image was taken by Voyager 2 when it went past, and it took this image, I'm not ashamed to say, just 2 months after I was born. I'm as old as this image is. And it's a fantastic picture of our most distant giant. Neptune is an ice giant. And this cloud that we're seeing here, that is solid ammonia particles in the atmosphere. It's so cold out there, almost everything freezes. And these storms are whipping around the planet at whopping speeds. Those are the fastest winds in the solar system. Can't get faster than that. But that's just our solar system. That's a statistic of 1. We can't deal with that in astronomy. We want lots of things. We need to start looking at all of the other stars. What else is out there? What other kind of phenomena have we not discovered yet? So, how about that? That's just an artist's impression of just a handful of the planets that have been discovered in the last 2 decades. There are now over 4,000 planets that have been discovered outside of our solar system orbiting other stars. If you look up in the night sky, over 50% of them will have planets. And those are just the ones we can see. The stars that we can't see have planets that number in the billions. More planets than there are stars. And we're just trying to look for them and trying to understand them. That really helps us try and understand our own solar system. Now, there's very few graphs in this talk, but allow me a couple. This is telling you the planets that have been discovered. At the bottom is their separation from their star, so how far away they are from their star. And up the side is the size of those planets, the mass of them. Now, to put this in context, I dumped the solar system on top of it for you. So we've got Jupiter up there in amongst those blue triangles. We've got Saturn, Uranus, and Neptune out there. There's nothing really that we've discovered in that space in the diagram. And we've got Earth down here. Now, the reason why we haven't discovered anything in these portions is purely to do with the techniques that we use and the ability of our instruments. It's not that they're not there, it's that it's really difficult to find them. And that's a little bit of a problem that we're trying to work out. But what you're seeing here in red are these transits, and if you've heard about the Kepler mission, Kepler was a beauty. It was so prolific at finding these planets, we're still trying to work out if some of them were real. It has in its catalogue thousands more candidate worlds that people on the ground are doing observations of right now, trying to work out if those are real planets orbiting other stars. So this number is just going to keep going up. This isn't steady. This isn't everything. This is just a tiny fraction of what is out there. But what I want you to focus on is this corner up here, away from Jupiter, in a very strange parameter space. In this corner of the diagram, we are so close to the star that we are 20 times closer than the Earth is to the sun. That's even 8 times closer to their stars than Mercury is to our sun. And we just said that the sun is bombarding Mercury's surface with huge amounts of radiation and particles. Mercury sits inside the sun's atmosphere. These are 8 times closer to their star than Mercury is. But also, the ones at the top here, they're as big as Jupiter. Take Jupiter, that 11 times the size of the Earth planet, and stick it right next to the sun. That's what we're seeing here in this top corner. This is showing us that there are these giant Jupiter-sized worlds. Now, to put that in context in something that you can go home and you can visualize and try and understand, I want you to imagine that the Earth was the size of a pea. Now, on this scale, if we had our nice Jupiter 11 times that size, it would be about the size of an orange. Some of these are bigger than Jupiter. You can see that. They go all the way up here. On average, these planets here are the size of a large watermelon. They're huge compared to what we have in our solar system. Now, you'll be hard-pressed to find such a beautifully spherical watermelon, but if you could imagine that, it's a little bit crazy. I find this is a very helpful, I call it my fruit basket of planets. The Neptune ones, if you wanted to look for something this size, they'd be about the size of a plum, nice purple world. And those are actually, if you look here, most of the planets that have been discovered are these Neptune-sized worlds. Neptune is 4 times the size of the Earth, and most of the planets that have been discovered are Neptune-sized worlds, or something that is slightly smaller, and something we don't have in our solar system to compare to. So there's a lot out there that we really don't understand yet. But how do we take this further? This is just telling us numbers. This is just telling us that there are other planets out there. We want to look a little bit closer. We want to try and understand those worlds. Now, what I'm showing you here is how we do that. We look for the light that has come directly from that planet. So we're seeing the emission from that planet itself, ignoring the star. Or we're looking at the starlight that has shone through that atmosphere before reaching us, and we get an absorption spectrum. So if that starlight is shining through that planetary atmosphere, anything in that atmosphere is going to block that light. And every single molecule has its own little absorption spectrum, its own little pattern, and we can look for those. It's the same in emission. They've got their own little patterns that we can look for. But the amount of light that is put out by the planet alone is very small, so that's very difficult to do. This, on the other hand, if that planet is passing directly in front of that star, we can do this. And we can do this by something called transmission spectroscopy. So take absorption spectrum. We are then shining the light through the atmosphere. It absorbs and transmits the rest of it, which is why it's called a transmission spectrum rather than the absorption spectrum, just to confuse everyone. It confuses everyone that isn't an exoplanet scientist. I think we did it on purpose. So what we're doing is we're looking at that planet as it passes in front of its star. As it does, it blocks out a very small amount of that light. If we look at that in lots of different wavelengths, if we build up our colors, we look at it in, say, I don't know, red or blue, we get a different amount of absorption because the atmosphere is going to be absorbing some of that light. And then we build up our colors, we get our picture, and we start putting it together. And we get the change in the amount of light blocked by that planet over different wavelengths, over different colors. And then we can start using some of the physics that we understand. We can use these spectra. Each element, each molecule has its unique fingerprint. If we piece that together and try to understand it, we can put a model to that and try and work out what's in the atmosphere. In this case, what it's showing you is some sodium and potassium there. What you're seeing over here is something that I recently did with the Hubble Space Telescope, and you're seeing this slope here from hydrogen and helium in the atmosphere. These are big, gassy worlds, mostly hydrogen and helium. You're seeing this sodium absorption, this potassium absorption, and most importantly, huge amounts of water vapor in the atmosphere. They're so close to their star, they're incredibly hot. They're about 1,500 Kelvin. They're very, very hot. Everything's in the gas phase. So what we found was there's lots of water. None of it's liquid. It's all happily floating around in the gas. These are boiling pots of material. So that's how we do that. Another way of showing this change in depth, is showing you how the planet appears to us. What it's doing is it's changing its relative size. It's changing the amount of light it's blocking out. So if we've got our model and we watch this, the planet looks like it gets bigger and smaller as it's absorbing that light. And that's what we're doing. We're looking for this change in the size of that planet as you go through all of those colors. I find that's a very helpful visualization. I even have to go back to it every now and again to remember what it is we're doing. So taking all of that, the techniques that we use, how do we do that? I've already hinted at this, but we need our eye on that storm. We need to be looking for this. How are we doing that? My favorite workhorse in astronomy, the Hubble Space Telescope. It gave me my PhD, so I'm quite happy with it right now. The Hubble Space Telescope has been an amazing tour de force of looking at these exoplanet atmospheres. And this is showing you 10 different planets. And you can see them happily rotating there. These are 10 different planets that we looked at with the Hubble Space Telescope, and we got that spectrum, we got those fingerprints from those molecules. But what we found was that these Jupiter-sized planets, all of them bigger than Jupiter, all of them about 20 times closer to their star than we are to the sun, so we would expect them all to be roughly the same. They're all different, of course they are. Why wouldn't they be? Nature's a pain. We have no clue. They are all different, and what we're seeing here is that they go from very clear atmospheres, so what we would expect to be finding, all gas phase, everything's a gas, it's so hot, it should be a gas, down to these ones which display really flat spectra. We don't know, there's something blocking that. What is blocking that? Down to these ones which show these huge slants, which shows that things are scattering in the blue end, and then in the red end, they're not. What is happening here? What I love about this little animation is that if you watch it carefully, you can see that they're all rotating at a different speed. And that's because they have different orbital periods. And their orbital period matches their rotation speed. We have that phenomenon here, the moon. The orbital period of the moon matches the rotation period of the moon. A year on the moon is the same length as a day on the moon. These are what is called tidally locked to their star. They have a permanent day side, which is always facing the star, and a permanent night side, which is always facing away. You have heat from the star bombarding one side, and no light at all getting to the other side of that planet. So that does some very strange things to a planetary atmosphere. And I'm going to take you through some of those later. But it's not just these 10 planets that we've looked at. This is just a smattering of some of the work that I've been doing. I've got more now where all of those gaps are, so I've got some work ahead of me. But what we're finding is that these giant planets, 80% of them show evidence that there is water vapor in their atmosphere. We're seeing this fingerprint of water gas in the atmosphere of these giant planets. Water is the third most abundant molecule in the entire universe. It's absolutely everywhere we look. And we need to really understand the balance of water in these atmospheres to work out where and how they formed. But unfortunately, we can't quite get there yet because we can't constrain it. A lot of these have very large uncertainties on them. That means that we can't precisely measure how much water there is. And only roughly 5% of them have this nice, precise measurement so that we can work out perhaps where that planet formed. Enter the James Webb Space Telescope. And for those of you who were here at the last one, we had a really nice presentation on the James Webb Space Telescope. It's going to be launching in spring of next year, and it is going to be a lot larger than Hubble. It's going to be a lot further away from the Earth, so we're not going to have the Earth's light getting in the way. And it's going to be looking in the infrared in a different wavelength. And what that allows us to do is look for different molecules. Instead of just looking at the water that we can see here, we're also looking for this carbon dioxide in the atmosphere. And that's really important for us to understand the balance between oxygen and carbon. This is just a simulation that was done by one of my colleagues, Natasha Batalha, and this is simulating the atmosphere of one of those planets that I showed you before. We're going to get absolutely beautiful precision data on these so that we can understand this planet's atmosphere. Where did it come from? How did it get there? What is it made of? Now, that's not the only one. There's loads of them that we're going to be looking at. This is just one from a DD, Director's Discretionary Early Release Science Time that has been awarded to the exoplanet transiting community. And we're going to be getting observations of this giant planet called WASP-79b. Great name. WASP-79b, from our observations with Hubble, which are in gray in the background there, this is what we predict we're going to be observing with the James Webb Space Telescope. Amazing precision there on the CO and CO2 features and the water. And what you can see here in red is what we understand based on Hubble data alone, and then in blue, how much better we would understand this planet's atmosphere just from adding these observations with the James Webb Space Telescope. So we have a huge amount to learn about these exoplanets, and it's all going to be coming in the next decade. We're going to know so much more about how planetary systems form and how a planetary system like our own formed. So that's all to look forward to. But let's delve into the atmospheres of some of these planets a little bit more. Explore some alien worlds with me. I want you to watch this video. I want you to tell me what you think this is. Sunrise. Beautiful sunrise. But that's the sunrise of this planet here. And that's the sunrise of the Earth to scale. What you'll notice is the colors are remarkably similar. What I think is immediately apparent is that it's a bit larger than what we're seeing here on the Earth. That is an actual size scale image compared to the Earth of what the sunrise would look like if you were in the atmosphere of a planet called HD 189733b. Telephone numbers. A lot of this audience will remember having to memorize telephone numbers. That's what we're doing still. HD 189733b, much like the Earth's atmosphere, scatters all of its light in the blue end of the spectrum. It scatters that light away. And if you were sitting looking through that atmosphere at its star, you would see this gorgeous red hue across the star, much like the Earth's sunset. You, of course, on this planet would be 20 times closer, so the star in the sky would look a lot bigger. And also, because you're so much closer to the star, you'd see all of the arrays of the colors of a sunset all at once. So it would be a beautiful spectacle. Now, of course, another caveat to this is that you'd be sitting in an atmosphere that it was at the temperature of 1,200 degrees. So you wouldn't be very happy. You would also be sitting in an atmosphere where it's tidally locked. So the only way you can see the sunset is to be sitting specifically at a point on the edge of that atmosphere between the day and the night. The boundary between the bright, sun-bombarded day side and the cold, frigid, lightless night side of this planet. You'd be looking out at that star and you'd see this gorgeous sunset. But that's kind of like the Earth. It scatters, it's a bit boring sunset. We've seen that one before. What about this one? This is a simulation of a sunset on a different planet called HD 209458b. HD 209458b has sodium in its atmosphere, and it doesn't scatter light like the Earth's atmosphere. It doesn't scatter all of this blue light. it's relatively flat, but then it's got sodium absorbing that light. Now, sodium is a nice yellow color. Street lamps are sodium lamps. They shine a nice orange. But if it's orange that's shining, that means that orange is taken out of your spectrum. So it's being absorbed. You're not seeing that through your sunset. So take out that orange and then see what the sun would look like, and it would look a nice alien green blue. This is what the sun would look like, or the star that I'm going to say it wrong. HD 209458 is the star, the planet is the bee. So this is what HD 209458 would look like from the atmosphere of the planet. Alien green. And that's because there's sodium in that atmosphere. Absolutely brilliant. But I want to take you back to this boring, mundane sunset right now, because this planet's more interesting than it lets it out to be. This planet has shards in the wind. It is, as I said, 1,200 degrees. 1,200 degrees. It is also being bombarded by an active star. What you're going to see here in this video is a flare go off on that star and a reaction from the planet. And this is a simulation that is done based on the data down here. This is showing us that when a flare goes off, and this was measured with an X-ray telescope, the flare from the star was measured, and then the planet was looked at during this time using a UV telescope, and what it saw was a really big spike in the Lyman alpha, and that's looking for hydrogen. Lyman alpha lines are created by hydrogen. And what we saw was this humongous tail of material that had been blasted off of this planet's atmosphere by this flare from the star. That's a violent place to be. Not only is it a violent place to be because of the star, but the winds on this planet, remember I said Neptune's winds, 1,200 miles per hour. The winds on this planet have been measured to be 5,400 miles per hour, whipping around that planet's equator in a huge band, speeds that are absolutely insane. You physically cannot imagine them. But because of the temperature of this planet's atmosphere, there's another issue. God, it's really a horrible place. The other issue is that there are clouds in this planet's atmosphere. Now, the clouds here on Earth are made of water. We like water. It's a bit painful when it's hitting you, when it's hail, or it's a bit cold when it's snow. These clouds are made of magnesium silicates. They're made of sand. But they're not made of nice beach sand that kind of hurts when it blows off the beach. These are made of molten glass. And that is flying into you at 5,400 miles per hour, horizontal winds of molten glass over 1,000 degrees. And then every now and again you'll get blasted by radiation from the star. I think that counts as wild weather. That's just the start of the craziness. This planet has been studied the most out of almost all of the exoplanets that we've been observing, so we know quite a lot about it. But there are other really wacky worlds out there that we're learning about. One of them is HD 80606b. And HD 80606b is essentially a Jupiter-sized comet. This is its orbit compared to our solar system. It comes in from up here, close to where the Earth orbits. So it's fairly decent, quite nice out there. And then it whips right down close to its star. This actually goes much, much closer. And then it slingshots out again. And then it comes back down. And then it slingshots out again. This is a cometary Jupiter-sized world. Can you imagine what that does to an atmosphere? We call this an engineering problem more than anything. In engineering, you hit something with a hammer and you wait to see how long it takes to go back to normal. Every time this planet orbits, gets hit by a hammer and we have to wait to see how long it goes back to normal. And actually, we've been making those observations with the telescopes. And we can do that measurement by looking at the planet over the course of this orbit and looking at how that atmosphere is reacting by measuring the heat. Now, I don't know if this video is playing or not. I think it is now. And this is a model of what happens to this planet's atmosphere. As it comes close to the star, it starts to heat up. It gets smacked in the face, and then over time, it settles back down again. And if you look towards the end there, you can see this bow shock coming around here. Just shock waves going around and around the planet as it tries to calm down and get back to normal. The adrenaline rush is kind of coming down. We're sitting nice and happily back out here, and then roller coaster ride and getting hit again. This atmosphere goes through extreme growing pains every time it comes close to the star. And it's on a 111-day orbit. So it happens quite often for it. And it's a great kind of test tube for us understanding the engineering of a planetary atmosphere. It's fluid dynamics in action. Crazy planet. Now, the next one is one of my favorites, and I think you'll find out why. WASP 12b. Not only is it easier to remember, bonus. But what we saw when we measured this atmosphere was this kind of slope again, like I showed you with that HD 189733. We saw this scattering from the blue end all the way down into the infrared. Now, the reason why this sunset's a little duller than we see in 189 is because it's scattering uniformly at all wavelengths. It's just scattering all that light, and it's a very film noir kind of sunset on this one. It's all very kind of mysterious. But this planet's even hotter than HD 189. This planet is 2,500 degrees on its day side. 2,500 degrees. That's hotter than sitting under that Falcon 9 as it was taking off. Sitting right underneath that. That planet is sitting in that temperature all the time. Now, what this scattering tells us is that there's something in the atmosphere. There's liquid droplets in this atmosphere. It's not all gas. At that temperature, everything we know of should be in the gas phase. There should not be any liquid droplets of anything in this atmosphere. So what this is telling us is that the temperature change from that day side at that 2,500 degrees to the night side where we're looking at this planet is huge. The night side where we're observing this has to be around 1900 degrees. There is a temperature change of over 500 degrees from the day side to the night side of this planet. That causes huge amounts of winds around the planet's atmosphere. But that also tells us a little bit about what these clouds might be made of. And there's only really one option left in this temperature range for what these clouds can be formed of. And it's a little thing called corundum, or more commonly known, sapphires and rubies. The clouds in this atmosphere are gems, and they are raining down in this atmosphere. Absolutely beautiful. And the reason why it's all of these colors, and the reason why rubies and sapphires are different colors, is because this corundum, this Al2O3, nice small combination of elements, if you stick a random metal from a different element, it changes the color. So if you stick a different element in, it could be green or yellow. And we find all of the spectrum of colors in this corundum here on the Earth as beautiful gems, rubies and sapphires being the easiest and nicest to make. So the atmosphere will be a rainbow of gems. That's why it's my favorite. It's just, I'll take it. I'll have all of them. So we've found some really strange worlds, and we've been able to look at them with this technique, and it's only going to get better in the future. As the telescopes get bigger, our understanding gets better, and more planets are found that we can do these observations of. It's really exciting for me because I get to just play around with all of this stuff and try and understand it and try and communicate to everybody here just how amazing nature's imagination truly is. So we want to go on an exploration beyond our own solar system. And we're moving outwards. We're moving past our planets. We're moving to another bit of our galaxy. we've only explored a tiny portion of where we are. This is just kind of going to take you through every bit that we've been exploring. Out from the sun, as it becomes a small dot, out to our nearest stars. And every single one of the lines on here shows you a line to the direction of an exoplanet that's been discovered. As we move out to our galaxy. Every single day, more exoplanets are being discovered. Every single day, we're learning more and more about these alien worlds. And in turn, learning more about our own solar system. It's not the end. There's going to be more. It's never the end. This is just the current look again. So this is the size of the planet versus the temperature of that planet. This is what we currently have thanks to Kepler and everything else that was not Kepler. In the future, so towards the end of this year, a satellite called TESS is going to be launched. And TESS is going to find planets all down in this range. Down in these smaller worlds, much more similar to the Earth. Down here. So we're going to be moving towards these smaller planets and trying to understand what a smaller planet, maybe not a Jupiter, actually looks like, what its atmosphere is like. And we're going to be finding colder planets. Colder planets are important. Their atmospheres are going to be very different from the ones that I've shown you today. They're going to have atmospheres that are filled with hydrocarbons, like Titan's atmosphere, filled with soots that are a bit of a pain, but are really interesting to study in the labs. They're going to be something we don't have in our solar system. And that makes it really exciting, because we don't have a test tube here where we can throw something at it. We have to learn remotely. We have to collect every photon we can. So I'm really looking forward to the future of exoplanets, and I hope you all keep an eye out for some of the most exciting discoveries that are coming, because we're going to be learning so much more, and there's going to be a lot more surprises along the way. If you enjoyed hearing me talk, I talk for about an hour once every month with some of my friends. As was mentioned before, I do a podcast called Exocast. I have a colleague called Hugh Osborne who does detections. I do the classification, so I'm actually looking at what these atmospheres might be like. He's finding the planets. And then my other colleague, Andrew Rushby, who does astrobiology. What is life out there in the universe? How can we find it? So the combination of us arguing, if you think that will be entertaining, is good. I do warn you, we're all British, so the accents might be a bit of a pain. But we also will be getting transcripts of all those episodes. But I just want to leave you with that predicted number of planets that we're going to be discovering, and just the thought that anything is possible. Thank you.
Okay, we have some questions for our speaker down front here.
Yes, is Neptune highly locked?
Neptune rotates.
All right, so I have to repeat the question for the online audience. Is Neptune tidally locked, or does it rotate?
So all of the planets in our solar system rotate.
So the question then follows, what then is the source of these 1,300 mile an hour sustained winds?
All right, so
pressure variations cause winds in our atmosphere on Earth. What is causing these pressure variations on Neptune to this extent?
all right, I want to actually add to that a question from the online audience. So what causes those 1,300 mile per hour winds on Neptune? And from the online audience, how are those winds measured on Neptune? What is your reference point, since there's no hard surface?
So the answer is going to be unsatisfying. I'm not entirely certain. I imagine it's something to do with temperature differences. Neptune has internal heating. That's going to be causing some differences. That causes differences in the vertical uplift of material. So if you're uplifting material, it's cooling, it's condensing, and then that's going to be driving the fluid dynamics of the atmosphere. In terms of a reference point, those clouds are very, very helpful. Voyager is not the only image we have of Neptune. The Hubble Space Telescope has taken some amazing images of Neptune, and some of the ground-based telescopes also, in lots of different wavelengths, have been looking at Neptune's atmosphere, trying to understand it. One of the really impressive things on Neptune is this dark spot. I showed you the one on Jupiter, which is this bright red spot. On Neptune, there's this big dark cloud region, which is kind of confined to a spot. And looking at that rotation, we know the rotation of Neptune, and we can see the rotation of these cloud structures, and it's different. So we can get this differential, is what it is, between the rotation period of Neptune and the material that we're seeing, able to detect in that atmosphere.
Okay. Over there.
These, when I think of storms, Earth-wise, I think of precipitation. Does these storms in the planets also precipitate?
So on these crazy weather that you're having, is it actual real precipitation falling down through the atmosphere?
So that's a really good question. From the models that we have, these 3D GCMs, they're all based on Earth GCMs, which have then been expanded and applied to these giant planets and to the planets in our solar system. And what they're showing us is that you get this heat from the day side causes these very huge upwellings. And then on the night side of the planet, at this kind of terminator region, you get these updrafts and downdrafts, these upwellings and downwellings, where you're getting this precipitation. And it's not only those vertical motions that are doing it, but this temperature contrast from the boiling day side around to the night side means that you could have something that is heated to a high temperature, becomes a vapor on the day side, and then as it cools down, as it goes around the planet, it cools, it condenses, it rains out. Sometimes it might even become an ice of some kind. It could be snowing rubies on one of these planets. And then as it goes round, as these winds carry it round, as these dynamics push it around into the dayside heat again, it heats up and it's being pushed up in the atmosphere as a gas, and then you get this cycle again. So you see these big upwellings and downwellings in the planetary atmosphere, where this material is just constantly being transported around.
Okay. Other questions? I thought there was one over here. There's one.
Why is the moon gravitationally locked with the Earth?
Why is the moon gravitationally locked to the Earth?
So the gravitational locking comes from just conservation of the angular momentum. And when we're looking at these hot Jupiters, what would have happened? They couldn't have formed there. So after they formed and they're spinning around the disk of the star, as they move inwards, as you spiral inwards, you've got to lose some of that energy somehow. And as you lose that energy, you reach this very stable state where your orbital period matches your rotation period. It's an incredibly stable position to be in. So the Earth and Moon system's a little different, because the Moon started as the Earth, got bombarded, broken off, formed in this spiral ring structure. And the most energy efficient way is to be tidally locked. However, the Moon's moving further and further away from us every single year, so there might be a point in the Moon's future where it is no longer tidally locked to the Earth.
I won't be around then.
All right, over here. Question.
You have these Jupiter and larger sized planets very close to a star. Is there a core that's holding them together, or are they just the aggregations of gas that have accumulated provides the stability? Because it seems like the energy being that close to the star is terrible.
So I'm going to summarize that in terms of, you got these hot Jupiters, these gas giant planets in so close to the star. Why don't they evaporate away? What's keeping them together?
That's a good question, and it's mainly the mass. There are actually some planets that have been discovered where we think they used to be these giant gassy worlds, but all of their atmosphere has got blown away. We see evidence of these very condensed, rocky cores of planets where they don't have an atmosphere, and they really should. So we see evidence that some of them have lost their atmosphere entirely. But as I said before, these planets did not form there. You cannot form a giant planet that close to a star. It had to have moved in from earlier in its system, earlier in the disk. It had to have moved in from further out. Now, there's a number of theories of planet formation, but first you need to stick together a load of particles. And as you stick together those particles, you accumulate gas around you from the disk. And it's this runaway accumulation of that gas which causes you to create a planet like Jupiter. Now, if that had then moved in towards its star, in these positions where they are, we've seen evidence that the atmosphere gets blown off. But we can measure how much, and it's very, very little. It's the equivalent ratio of a CME coming off of our sun. It's losing a very small amount of its mass in any one time. So it's not something that's going to completely wipe out HG 189.733b's atmosphere, based on the measurements that we have. So it's really the mass that's holding this atmosphere on. It's clinging to it. And every planet, even our own planet, has something called a Roche lobe, which is a gravitational distance away from that planet where something is no longer gravitationally bound. If the gas was energized enough so that it got outside of this Roche lobe, it would escape forever. It wouldn't ever come back. If it was energized such that it kind of escaped and then it fell back inside this Roche lobe, then you wouldn't ever lose that bit of the atmosphere. So there's a number of things there that are kind of keeping it in.
All right, all the way in the far side of the room there.
Found any exoplanets with a binary star system, and how does that affect?
Have we found exoplanets in binary star systems, and how does the presence of the binary affect the planet?
We found planets in binary stars, in triple stars, and in quadruple star systems. So binary stars are the most common in our galaxy, and there's quite a few planets that have been discovered around binary systems. WASP-12b, the one that I showed you at the end, is in a triple star system. WASP-12 only orbits one of those stars, but also orbiting that one star is two tiny little stars, M stars, that orbit each other and orbit that star. So it's in a triple star system. It's a freaking brilliant world. That's also a pain when you're trying to do data analysis because there's two other stars right there. But yes, we found planets and multi-planet systems around stars. And that really tells us about our own solar system and how possible that is. And some of these have interactions, and some of them don't. And that's really important for us to try and understand. And it's an area that we're really pushing into.
Okay, down here.
The difference between day and night temperatures on some of these, what would that range be?
All right, so what is the range of day and night temperatures on these really hot planets?
So that really depends on your dayside temperature, the orbital period of your planet, because the orbital period of your planet defines your rotation period of your planet. And the rotation period of your planet defines how dynamic the atmosphere is going to be, because that's a good driver of an atmosphere. So on some of the hottest ones, we expect that day-night contrast in temperatures to be in the range of 500 plus degrees. But on some of the cooler ones, and I say cooler because my temperature scale is completely wacky, HD 189 is a nice cool planet at 1,200 degrees. And on that nice cool planet, the temperature difference between the day and the night is only about 50 to 200 degrees. So it ranges based on the orbital period of that planet and the heat from the star. So a bigger star, a hotter star, will also be putting out way more heat, and therefore you get a bigger contrast there.
And are those temperatures
We're
your...
talking about Fahrenheit degrees?
Yes.
Kelvin.
Yes.
Okay.
So centigrade degrees. Almost.
It's very hot. Sorry, I don't do
Yes,
Fahrenheit.
astronomers. That's what was my question too, because I know astronomers always work in Kelvin and
I
such.
can give you Celsius. I can't give you Fahrenheit. I'm learning. I'm really trying to learn.
All right. Question there.
I'm interested in the time scale of variations in the conditions on the planet. You know, the Earth has been roughly the same for billions of years, and how can you tell anything about many of the planets? How long will their atmosphere last? Will the temperature stay the same, and so on?
So really, he's asking research questions. Can we tell how long the atmospheres will last on these planets and other characteristics like that?
So these planets are fairly old. They've been like this for a really long time. And as I said, they're not losing a huge amount of mass from their atmosphere. The planets that we've observed where they appear like they've lost all of their atmosphere, that clearly happened very early on and very quickly. So it's not expected that these giant planets will lose a humongous amount of their atmosphere at all in the lifetime of us looking at them the way that we are. In terms of intrinsic variations, weather patterns, that's a lot harder to do. One of the reasons we look at those really eccentric planets that I showed you before, that comet planet, HD 80606b, is because we can look at this variation over time of what an atmosphere does at different distances from a star, just from having one system. these are fairly consistent from what we have. The other problem with that is your measurement has to be so precise at every time you measure it. So if I measured it this year, and I got a really nice measurement, and I measured it next year and it was different, and then I measured it the year after and it was different again, I need to know that it's not the way that I'm doing my data analysis. I need to know that it's not something in the telescope. I need to know that it is actually something in that planet's atmosphere that's causing that, rather than something that we as scientists have done to look at that data. So it's really hard to say whether we've got any kind of small weather patterns. One of the really good examples of looking for these kinds of weather patterns is brown dwarfs. Now, brown dwarfs are much further off this diagram. They are roughly the size of Jupiter, but they're much, much more massive. They're over 15 times the mass of Jupiter, and that is a lot. These brown dwarfs aren't quite stars, but they're not quite planets. They're actually burning at their core deuterium. And in these brown dwarfs, there's this transition between different masses and ages of brown dwarfs where we see these patchy clouds in the atmosphere and the rotation of those clouds. So you can see and measure this weather pattern in a brown dwarf's atmosphere because you're doing the opposite of what I was explaining at the beginning. You're doing the emission spectrum directly from the brown dwarf rather than the absorption spectrum through the atmosphere. So it's the different techniques which allow you to kind of look at these different systems.
Okay, we had one question online that wanted to know what is the force responsible for producing that beautiful hexagon pattern on Saturn? They were speculating that it was the moons, and I was like, no, it's not the moons. Do we know the hydrodynamic forces that produce that beautiful hexagon pattern?
Fluid dynamics can do it. We see that hexagon pattern appear in multiple places on the Earth. That hexagon pattern appears for a number of different reasons. It's a very stable pattern. It's a very strong pattern. The way in which fluid dynamics works, we really don't know specifically for Saturn what those driving forces are, but we see that pattern here on the Earth. Mathematically, it comes out of a lot of solutions. I don't know if anyone knows the Devil's Causeway in Ireland. It's the columns of basalt for the volcanic material form these hexagons. And they form hexagons because when you're cooling a material down, that is the most structurally stable shape that something comes into because of the structure of the materials it's made out of. So there's a huge number of things that make this hexagon pattern. We're still trying to work out exactly what's going on, because that is on a scale that we can't produce here on Earth.
Right, yeah. And I'd seen a laboratory experiment that produced a hexagonal pattern from resonances, but it wasn't really a proper analog for it. So
yeah, so you have to, when you're doing these analogs, you need to get the pressures right, you need to get the temperatures right, you need to get the materials right. The problem with Saturn is it is hydrogen-helium atmosphere at high and low pressures, and you are not allowed, or you will not be funded to have a lab that will almost certainly explode. So it's a little bit hard for us to simulate, so that's why we do it in computers, and that's the way we kind of really explore these worlds.
All right, so I think there was one more question right there. Okay, last question for the evening.
In systems where there's multiple stars, are there any planets that would orbit one star for a while and then switch over to the orbit of another star?
So the question is, in multiple star systems, can planets switch from orbiting one star to the other star?
Not that I know of. There are three types of binary systems that I can explain to you. There is, imagine your two stars here. You can have a binary system where you've got a planet orbiting just one of those stars. You can have a planet orbiting both of those stars. And you can have, technically, we haven't found one yet, technically a stable orbit where it does this. So you get this smiley face. You can have it here, you can have it here, you can have it here, or you can have it here. The smiley face of binary systems. I don't know about this one. You'd have to play that, what's that game called? That simulator for Gravity Simulator. That would be fun, but
It really strikes me that the dynamics really it'd go chaotic, and it wouldn't be stable.
Most likely spin off.
Yeah.
Early in the history of these binary systems and different planetary systems, we know that stars kind of come by. We have evidence that stars have passed our solar system pretty close. Stars are pretty evil. They will grab your planetary children and take them with them. So we have evidence that some of these planets that we're looking at have been grabbed from somewhere else. They've been nicked from their parent star. So there's lots of different ways in which you can get these configurations, but we know that the formation of planets, we know that the formation of stars, and we know that the dynamics of our galaxy is very, very chaotic and dynamic. So there's a lot of things that can happen.
All right, so lesson for you. Hold on to your planets, okay? All right, so next month on March 6th, Mia Bovo will be talking about mapping the United Federation of Planets and Astronomers Guide to the Galaxy. And let us give Hannah one more big round of applause.